Part A. Write an expression for the equilibrium constant Kp for the reaction. Okay. In order to find the equilibrium constant, you will have to use the pressure of the product over the reactant. You must use parentheses for the pressure. And remember that the powers are the coefficients of the elements.
Number 2, Part B, number 1. Calculate the value of the reaction quotient Q at these initial conditions. So for this one, we're going to plug in these values right here as they are initial pressures in the Kp. So, let's start off. Now, we're going to plug in the NH3 ATM for the top one right here. Now, we're going to write the other ones, starting off with N2. And now, H2. Let's not get ahead of ourselves here. As H2, it's cubed. Now, for this, we're going to plug this into a calculator. Calculate. Oh, wow, that was really fast, class. Oh, and looks like our answer is 0.166. We rounded up because of the significant figures. There are 3 here, so there's going to be 3 here. Now, Part B, number 2. Predict the direction in which the reaction will proceed at 700 Kelvin. That the initial partial pressures are those given above. Justify your answer. So, our initial Kp value for the equilibrium constant was 3.1 times 10 to the negative 4th. Now, if we compare these two, we will see which one's bigger. This one seems bigger than this one. And this is our Q. Now, because our Q is bigger than our Kp, the reaction will shift to the left because more products are made. This will balance out the equation as more reactions need to be produced to balance out the great amount of products that are produced.
Part C. Calculate the value of the equilibrium constant, Kc, given that the value of Kp for the reaction is 700 K, is 3.1 times 10 to the negative 4th. Now, the T is 700 K and the Kp is 3.1 K 10 to the negative 4th. This equation is given to us on our blue little paper thing.
That was yellow.
It's on both. Now, we are trying to find the Kc, so we need to manipulate this equation in order to have it so that Kc is going to equal what we're going to get. So, you must first divide this into this. Okay. Now let's plug in our numbers. The so the Kp is 3.1 times 10 to the negative fourth. And it's over R, which is always going to be 0.0821 and is given to you on your yellow or blue sheet. And then our temperature. And that is both powered to the delta N, which is you're minusing this, the coefficient of the product minus the coefficients of the reactants, which is -2. Okay, now let's put it into your calculator.
Calculate.
Okay. Now you have the Kc equals 1.0. Go.
Okay, this is number 2, 1di. Okay, the question is, it says the value of Kp for the reaction represented is 8.3 times 10 to the negative third. Calculate the value of Kp at 700 Kelvin for each of the reactions represented below. For part 1, this is what you're given, and this is what you started off with. If you compare the two, you'll see that this is the reverse reaction of this. And the equilibrium constant of a reaction in the reverse direction is the inverse of the equilibrium constant of the reaction in the forward direction. So in order to get the equilibrium constant for this one, you would just do the inverse of the reverse reaction. So in order to do the Kp, you would just do 1 over what's already been given, 8.3 times 10 to the negative third. And then putting that in your calculator,
Calculate.
you should get 1.2 times 10 to the second. Okay. Now, part 2. This might take a while. Okay, for part 2, you have to use Hess's law to get the equilibrium constant. In the very beginning of this question, you're given this equation, and then for D, you're given this equation. Now, you know the equilibrium constants for both of them, and you have to try to find the equilibrium constant for this new equation. Using Hess's law, you would add these two individual equations. So, you would do N2, they're all gases, plus 3H2 makes 2NH3, and NH3 plus H2S makes NH4HS. Is that right? Yeah, okay. So now you're given the Kp up here. I'll write that down then. Okay, so these are the two equations, and ultimately you're trying to get to this. Using Hess's law, you would see that when you add them together, everything's on the right side, nothing's going to be flipped. But if you notice here the 2H2S and the 2NH4HS, which means that everything here is going to be multiplied by 2. And if a reaction has been multiplied by a number, the equilibrium constant is raised to that power, which means that this would be squared. Also, the equilibrium constant is the product of the equilibrium constant for the individual steps. So you know, if we add this together, nitrogen 3H2 plus 2NH3 plus 2H2 2s will give you h3 plus 2h4hs. Okay, now the ammonias will cancel out, and you're left with the right equation. Okay, so then now all you do is you multiply the KP's together in order, so 3.1 times 10 to the negative 4 times 8.3 times 10 to the negative 3 squared. And then your KP equals 2.1 times 10 to the negative 8th.